One of the things that you might care about is they apply to investments. Does that idea make sense? Yeah. So the fee paid to use somebody else's money, this is called interest. Interest. So like when you take a loan from the bank, you pay the bank interest. When the bank takes your money, they give you interest. And it's computed as a percentage called the interest rate, yep, of the original amount called the principal. That might also be called the like initial investment. And so here's like how it works. Like suppose like, you know, I borrowed $150,000 to buy a house, right? So then
Small loan of $1 million.
small loan, 100 was a reasonable loan, but the bank say, you know, they continuously earn interest in the money that I've given them, right? So this is actually called compounding interest. So it's like if you invest $1,000 and you get 5% interest, then you get another 5% interest on the money you've earned from the bank, like after like another year. And these are pretty simple cases. The cases where you like say have a loan and start to pay stuff back, a little bit more complicated because you decrease the amount that you're earning interest on. So suppose, just a simple case, suppose you invest $10,000 for 4 years. What is the difference between compounding annually and compounding quarterly? So we're going to look for a pattern. So at the end of year 1, how much money would you have? How would you figure it out? Oh, I'm sorry. I forgot to give an interest rate. Let's say 2%.
Yeah, I was confused there.
I put that in my notes and forgot that I'd forgotten to put it. Okay, suppose we have $10,000 for 4 years and 2% interest rate. So at the end of year 1, how would you figure out how much money you have?
2% of 10,000 and subtract it from 10,000.
I don't think you subtract it from 10,000. You earn this much money.
Oh, yeah, it's interest, so you add it. Yeah.
You add it. So
Multiply by 1.02.
yeah, I think it's a better idea to multiply by 1.02.
Yeah, you can do that too.
Does that make sense? Because the 1 means you get the 100% of what you had, right? Plus 2% more. Does that make sense?
Mm-hmm.
Okay. So I don't know what that is, whatever. That's how much I have at the end of year 1. How would I figure out how much at the end of year 2? I'd take that number and I'd multiply it by 1.02 again, right? So I had this much money, that 10,000 times 1.02, and I earned 2% again, so times another 1.02, right? So that's 10,000 times 1.02 to the second, right? Does that make sense? At year 4, how much are you going to have? 10,000 times 1.02 to the fourth. And that's about $10,824.32, approximately. And that is compounding once per year. I mean, you get your interest at one time at the end of every year. Most loans and bank things don't work that way. I think a lot of them, including the loan on my house in particular, compounds quarterly. So what that means is you take that 2% and you divide it into 4 pieces. So what is 2% divided by 4? 0.5%? Mm-hmm. And what you do is you get 0.5% after the first quarter, so first like 3 months, and then you keep that money and you get another 0.5% on that. So you divide your 2% interest into 4 pieces. So how this will happen is after 1/4 of a year, you're going to have 10,000 times 1.005. Does that make sense? How about after half a year?
1.005 squared.
1.005 squared. And how about after 3/4 of a year? it'll be 10,000, 1.005 to the,
Third.
and then the last one after 1 year, it'll be to the fourth. I think I put too many zeros there. Which one do you think's gonna be more money? How about you calculate what that is? You guys all calculators, you all have phones. So calculate what 10, and that's actually only after 1 year. How many, what would the power be if it was 16, if it was, I just gave you the answer, 4 years? It'd be 16. Okay, so after 4 years, it'd be 10,000 times 1.005 to the 16th. So figure out how much that is. Get your calculators out, because it's going to be helpful if you know how to push the buttons, okay? Like, I know it's like 10,830, I'll say 30.71. Since it's money, let's give it 2 decimal places. Does that make sense? So the more often you compound, you're going to have slightly more money in that case. And it's because the 2% interest you earn, you sort of earn part of it first, then you earn interest on the part that you've earned. That's why it ends up being more money. Okay, so that's a sort of specific example. The next thing that we have is the formula that works for any kind of compounding. So what if I'd compounded monthly? What would have changed?
You have to change the first one would be
Over 12. And in a year, how many compounding things would you go through? 12. So in 4 years, it'd be 48 of them. Does that make sense? Okay. So that's what this formula on the next box says. So you have an initial investment, P. It's invested at an annual rate, R. Notice that R must always be given in decimal form. It's like when you use R in these formulas, make sure it's going to be given as a percent, but put it into decimal form. Compounded M times per year. The amount A in the account at the end of N compounding periods is this. So like in ours, we had 10,000 times 1.005 to the 16. That was what we had for the particular problem we're looking at. This 0.005, that was 0.02 divided by 4, right? And this 16 was that we did 4 years times 4 compounding periods per year. So that's what this formula just does in general. If I give you this kind of question on a quiz or test, I'm probably going to give you the formula. It also can be expressed as the second one that I circled. So instead of saying n compounding periods, you can take m, which is the number of times it compounds, times t, which is how long. So if you do monthly, which is 12 for 4 years, what would that exponent be? 48. Okay, so let's do this one. Suppose you invest $4,000 in account paying 5% quarterly. How much money will there be in 15 years and in 3/4 of a year? So I personally prefer the P times 1 plus R over M to the MT formula. That's my personal preference. And in that thing, M is the number of compounding periods. Okay. All right, so in this first case, what goes in for P?
4,000.
4,000. Okay, 1 plus, what goes in for R?
0.05.
0.05. And if you compound quarterly, how many times per year is that?
4.
4. And the power is number of compounding periods, and then does it say how long?
15 years.
15 years. What is 4 times 15? 60.
Why do you divide 0.05 by 4? It's
paying 5% quarterly.
That's a coin.
Quarters, 4 quarters in a year.
Yeah, but wouldn't it be multiplied by 4? Is it 5% per quarter, or is it?
Oh, yeah.
It's
annually?
5%, it's a 5%, 5% quarterly means it pays 5% and then compounds quarterly.
Okay.
It does not mean you get 5% each quarter.
Yeah, it's confusing.
Oh, God, no, yeah, no, you wish,
That's not right.
yeah, and certainly not now in this sort of financial climate.
20%. 20%.
That'd be 20% annually, yeah, there's just no way, yeah. I mean, in the 80s, that's how much like I think that when my parents bought a house in the 80s, the interest rate they paid was like 18%. It was nuts. So what do you guys get? You put this in the calculator. Because now the big thing is, can you actually punch these in calculators? Or if you have iPhones, can you punch them in iPhones? Or other fancy devices? I'm not going to take your phones away. Yeah.
How is this part of the calculator?
Hmm?
You plug the whole thing into the calculator.
It depends on the calculator that you have and how smart it is. Does that make sense? But you can plug the whole thing in a calculator. One thing that could go wrong is that if you haven't multiplied those, you've got to put them in parentheses. Okay, does that make sense? But try to plug it in and let's just see if you can get the same thing that I got. Because I did it, I have the answer, but I want to see if you can get it. If you're iPhoning, I'm pretty bit clever. I'm not 100% certain how your phones work. So what'd you get?
8,428.73 cents.
Yep, 8428.73. That's what I got as well. So just see if you can get that. Did you get it? Okay.
What was it?
8,428.73. You got that as well? Okay, good. This is one instance where calculators are definitely better than iPhones because the iPhone calculator is like really dumb.
Depends on the calculator you have.
If you can get a different calculator app, then perhaps it's better. But the one I've seen, you have to really know how to do order operations
Well, it depends on
correctly.
Both. Which calculator?
Obviously. Okay, 4,000. Now what if you do 3/4 of a year? What changes?
The power.
The power, exactly. So the power would become, it was 4 times 15, now it's gonna be 4 times 3/4. What is 4 times 3/4? That'd be 3, right? Okay. When I'm writing these things down on my slides for you, I will put parentheses wherever you would need them if you wanted to input this in a calculator. Does that make sense? So like, if you put this in right now as is, if you don't put the power in parentheses, it will raise this to the power of 4 and then multiply by 3/4. Okay, so either put it in parentheses or multiply out what it will be before you plug it in. So like that could be a 3. Yes, Tani?
For the time, we always just put exactly what it says up there, like if it's at a half, you just put a half.
Yes, exactly, yep. Another way you could do the time is you could just go straight to the 3 by saying this exponent is the number of compounding periods I go through. And since it compounds quarterly, that means that there are 3 of them that happen in 3/4 of a year. But personally, I've taught this before, and the way I taught it was to use number of compounding periods times time. They're the same thing. So like Alex might show you a slightly different, way to do it, but it will be the case that your exponents will multiply together to be the same thing that they give you right away. What'd you get for this one if you calculated it? 4,151.88. Awesome. Okay. So I think example 3 is a pretty relevant question, like for you guys in your lives. Do you agree? So it's better to pay things in cash because you don't pay interest on them, right? So suppose you want to have $25,000 in cash for a new car 5 years from now. How much do you want to place in an account so that you'll have that much money if your interest rate is 4.75% and it compounds weekly? Okay, so let's fill in the things that you know. So you have this A equals P1 plus R over M to the MT formula. Do you know the amount you want to have? Yeah, so that goes in, that's 25,000. Equals, do you know the amount you should invest?
No.
No. Do you know your interest rate?
Yes.
Yes, and what is it? So what number do I put in for R?
I don't know how many weeks are in a year.
4, 7,
You don't know how many weeks are in a year?
52.
52.
It's not 53, it's almost 52.
Definitely 52. M is number of compounding per year. It's like if you compound quarterly, that means it's like 4 times per year. Monthly would be 12, and weekly is 52. For daily, you'd use 365.
Oh,
Does that make sense?
yeah.
Okay. And then 52 goes in for M. What goes in for your time? 5. Okay. Now I know it looks wacky, but this thing, that is just some number, right? So if you knew what number it was, you could do 25,000 divided by that number, right? Okay, so what did you get for that number? Give it a lot of decimals, but so work it out, see what you get. It's gonna be 1 point something. Anybody get 1.126 and stuff?
How far should we go?
I took all the ones that I saw. Do you know that there's this thing called like the answer function in most calculators where if you have an answer, like you just push, and then you just push divided. Well, this will be a little bit different, but anyhow. So now just do 25,000 divided by that number, and you get P is equal to approximately 19,717.05, or about 19,717. So in most calculators, it saves you time not to punch every single little digit in. Does that make sense? There's a little button that says ANS. Do you see it on there anywhere? Depends a little bit on what calculator you have. That uses the previous answer that you had, and it takes all the decimals for you. Does that make sense? So if you do 25,000,
So I can clear it.
push divided by, don't clear it, and then divide it by, and then select that ANS. You should get this. See if it works.
It says ANS, but then 19717.
Yeah, it worked.
Cool. All right.
Okay, so that saves you time having to like actually punch all those digits in. Does that make sense?
Yeah.
Yeah. And it will use the answer that it previously calculated. Okay. So I have to find the example, I'm gonna dredge it up over spring break, but there's an example where if you do these problems and you do round and you compute interest, that you get vastly different answers. So like banks and stuff, they hold all the digits and they don't round until the very, very end when they have your money. Yeah.
Say a calculator like mine does not have an AS button, would it be under another abbreviation?
I'll look at yours after class, I'll try to find it, okay? Yes.
So when I did this in Algebra 2,
Mm-hmm.
our teacher made us do like, if it was compounded like millisecond and second and all that, and like, are we gonna have to do that or no? 'Cause
We're gonna get there.
We're gonna have to.
We're not gonna actually do milliseconds.
Okay,
But that person was trying to prove a point, and the point is on the next page.
okay.
So yeah, so,
'Cause that was difficult.
yeah, no, we're not actually gonna do milliseconds. Yes, Tani?
The answer that we got here, what is the answer?
Yeah, that is how much you had, you solved for the P, which is how much you've invested initially. So if you wanna have $25,000 after 5 years at an investment rate of approximately 5%, because that's about 5%, you have to invest about $19,700 to start.
Oh, in 5 years.
And then 5 years, if you leave it alone, don't touch it, you'll have $25,000. Does that make sense? Okay, great. So now Tyler had a spectacular point. So from the examples that we did, you saw that if you compound more times per year, you earn more money, right? So what his teacher did is they made them compound like every second and every millisecond, which is like kind of crazy, right? So what his teacher was trying to explain to them is that they want to explain what happens as the number of compounding periods you have increases to be an infinite amount. That's what they were trying to get at. So I'm gonna show you where this formula comes from. Remember that we talked about that E number yesterday, and E was what happened to this expression? As n goes to infinity and gets bigger and bigger and bigger. It's an irrational number, and it's approximately 2.718. So it turns out that when you do this thing, when you take the number of compounding periods and make it like 1,000, a million, a billion, a trillion, it becomes close to this number and makes this formula people call the PERT formula. Okay, and here it's a little bit tricky, but here's why. Okay, so you start with this, P equals, oh shoot, that's not right, A equals, sorry. A equals P 1 plus R over M to the MT. Seriously, guys? Totally not helpful. Okay. And we're going to look at what happens as M goes to infinity. So as the number of compounding periods you have gets bigger and bigger and bigger. So here is the tricky trick. This is 1 plus 1 over M over R to the M over R power times RT. This is not something that I think you would be able to come up with on your own, and quite frankly, I had to look it up. So, does it make sense, at least, that 1 over M over R is the same thing as R over M? Does that make sense? Does it make sense that M over R times RT is the same thing as MT? Yeah, they're the same thing. I don't need you to come up with this on your own. I'm just trying to justify why that becomes an E. You define a new variable. You say, I'm going to let N, or let's say equal M over R. And that becomes P 1 plus 1 over N to the N all to the power of RT. And then as M goes to infinity, shut up, this N, which is equal to M over R, is also going to go to infinity. So if the number of compounding periods gets bigger, your N variable is just the number of compounding periods divided by a rate, and that's also going to get big. It might not get big as quickly because you probably divided by like some number, but it will get big. And that's the reason that this thing becomes an E. So that's the technical mathematical reason. Because that is what E is defined as. It's defined as what happens to that expression when you plug in bigger and bigger values. So you're not going to have to reproduce this. What you really have to do is notice that this is what happens when things compound continuously. It applies to population growth. So it comes up in all sorts of applications. And there should be an E button in your calculator. And it will be a lowercase e, not an uppercase E. So see if you can find one. It might even be an E caret button. Depends on the calculator a little bit. The E with the X above it probably will work. Yep. Okay, so let's try one. Let's just compare compounding annually versus compounding continuously. So you have something for 5 years. You invest $1,000, and for some reason you got this awesome 12% interest rate. Super lucky you. So if you compound annually, A equals P 1 plus R over M to the MT. In the case of annually, how many compounding periods per year is that? 1. So M will equal 1. And that will be 1,000. 1 plus 0.12 over 1. Is it necessary? What's the power? Times
Oh,
5,
years, yeah.
because 5 years. So when you calculator that, because every noun can be a verb, what do you get? 1762.34. And as long as we're talking about money, unless otherwise specified, I think it's wise to give it 2 decimal places, right? Because that's how we do money most places. So that's annually versus on the other extreme continuously. So that's A equals P e to the RT formula. So you still plug in 1,000. This E is a number. Put parentheses around your rate, which is 0.12, times the time, which is 5. So try that E to the whatever button you have on your calculator and see if you can get it. If it doesn't put parentheses there after the exponent, do it yourself.
1,822.
You should get 1,822.12. Let's just verify that you can actually do that. Did you get it?
Yeah.
Okay, great. Look at who can calculator. You so proud? Okay. All right. Notice that there is, I mean, after only 5 years, there's a pretty substantial difference, isn't there? I think so. And it turns, if you go an even longer time, the difference gets greater and greater and greater as time goes on. Okay, so that's the money stuff. The other stuff we're going to talk about are doubling times and half-lives. So the first one we have is a doubling time thing. So in a 2008 estimate, the population of Nicaragua was about 5.7 million. And the population is growing quickly due to a high birth rate and low mortality rate. If the population continues to grow at the same rate, it's going to double in 37 years. So at this rate, what will the population be in various amounts of years? So I'm actually going to do part B first because I reconsidered and think that's the best one. We're going to get a formula first. And the way to do it is just to think about it a little bit. There's going to be a pattern, but I want you to understand it. So at the start, your amount is 5.7 million. There's no need to add in all the zeros. You can just have your answers be given in millions, okay? After how long will you double? So if T is 37, what's your amount going to be? What's 5.7 doubled? 11.4. Awesome. And after another 37 years, you're going to double again, right? So an additional 37 years is after 30 plus 30, 60 plus, I think, 74 years. Is that right? What's the amount going to be then? 22.8. This also assumes things don't change, right? Because the birth rate might go down or something. Or the death rate might go up. There might be war, genocide, whatever. You know, things might happen. But does the idea that every time 37 years passes, the population doubles make sense? Okay. And since as the T increases, you're doubling a larger number, the rate at which this is growing is getting faster and faster and faster, right? Okay. So we start with an initial amount times 5.7 million, and you multiply by 2, right? But you multiply by 2 after 37. Does that make sense? So you need this to be 2 to the first when you plug in 37. So the way you accommodate for that is you do x over 37. So just tell me if you think that that matches up with the things that we have. When you plug in 0, you get 2 to the 0, which is 1, right? That gives your start being 5.7 million, right? When you plug in 37, you get 5.7 times 2, which makes that, right? Does that make sense? When you plug in 74, what is 74 divided by 37? 2, right? And you get 5.7 times 2 times 2, which makes us 11.4. So the general formula is always going to be this. It'll be, can I just use P for start, because it's kind of like a principle of people, times 2 because you're doubling, and it's always x or time divided by whatever your double time is. Do you see what I mean by that? You have your start at 5.7, right? Because you're doubling, this is a 2. If you're tripling, it would be a 3, right? If you're halving, it would be a half, right? And you always take time variable divided by the amount of time it takes to double. So that's the general formula. Because these years are easy to figure out because you know that they'll double, right? But 34 isn't one of the nice even ones, is it? So now that you know that formula, how would you figure out how many people there were going to be in 34 years? Plug in 34. So A would equal 5.7 times 2 to the power of 34 over 37. I didn't actually need parentheses there, but in the exponent you do.
So if the number for doubling is different, then we just put that under.
If the number for doubling is different, the denominator changes. Is that what you were asking?
Yeah.
Yes, okay. Exactly. If the doubling time had been 10 years, it'd be x over 10. Okay?
The exponent is only to the 2, not to the 5.
The exponent is only to the 2. Yes, the exponent is only on the 2, not on the 5.7. That is correct. Yep. You should get, and it should be awfully close to having doubled because 34 is awfully close to 37, right? So I got 10.78 when I rounded. And it is in millions, so 10.78 million. How about 15 years? 5.7 times 2 to the power of 15 over 37, and I got 7.55. Good? Okay. But I'll move that down so you can see it better. The general formula will always be something like this. You can actually, it's kind of, we don't know quite enough math yet to figure this out, but you can actually do all these things with ease as well instead of 2's. You just need to know a little bit more as to how to like figure out what's in the exponent there.
Is that one we should have memorized?
It probably would be a good idea because that is definitely a question that's on your quiz. Like there's one question about doubling, there's one question about half-lifing because I think they're useful things. Okay, now a lot of the other questions that are on your homework and probably on Alex, they're just going to use this PERT model and you're just going to have to, plug in numbers in the appropriate places. Okay, so often people use this A equals PRT. You can also use this to model various population growths. It's just that they occasionally use different variables. So they will write this formula occasionally as A equals A sub 0 e to the kt. I don't know why they choose to use different letters. They just do. But the whole sub-zero thing is actually a really common sort of mathematical term, and I'm probably going to say this and not realize it. I'm going to call it A naught. So I think the subscript 0 is almost always read naught, and it's not NOT, it's NAUGHT. Have you guys heard the phrase, it's all for naught? So that's kind of where it's coming from. It means the starting place. Kind of like principal was how much money you began with, okay? And they just use a K instead of an R. I don't know. Just, this doesn't matter. They're different letters, but they mean the same thing. So A sub 0 or A naught is the initial or starting population. And I don't mean beginning of time, I mean beginning of when you start carrying. Like we didn't, start counting at year 0 when we talked about Nicaragua. We started in 2008. Does that make sense? That was our beginning point. And R, which is K, that is the rate of growth. So just squeeze this above this. So if I told you that a population is growing at 2% per year, and it starts with, 1.7 million, the equation would be 1.7 e to the 0.017 t. I did not do that right. Crap, I'm sorry. So the 1.7 is what you start with. In the exponent goes the rate, 0, 0, 2t, not.
So we're just learning another way to see
This, yeah, and this one assumes the whole, the population doubling, also you can assume continuous growth, but this one will be like, it's growing continuously at blah rate. And you can actually make the one with the 2 into this one, so it depends on how the question is phrased. So some questions will be phrased in terms of doubling time, in which case you use 2s, because that's what, multiplying by 2 is what doubles, right? If it's a growth, a rate of growth, like 2%, then you use this. You say, oh, it's like continuously compounding interest. It's the same thing, it's just you're compounding people and not money.
Okay, but the A equals PERT.
Applies to this.
Example just showing us that A equal A.
That's just often how the formula is rephrased for populations. But they really mean the same thing. Does that make sense? Okay, awesome. So like this one, we're given an equation. So you have this intestinal disease cholera, which is gonna be crazy, and it multiplies exponentially by cell division. So unless you find some way to sort of thwart its spread, you're gonna get sick. So suppose you start with one bacterium. How many bacteria are present in 5 hours? So this growth rate is huge. Remember how we said like 0.02, that was a 2% growth rate, right? In this one, we have 1.386. What is that as a growth rate?
138%.
138.6%, right? Okay, so it's growing really, really quickly. I know. So in just 5 hours, if you don't like use your Lysol, you start with 1, right? So 1 e to the 1.386 times 5. Ooh. So tell me, plug that in a calculator, how much you get?
1,023, because you can't have half of that.
Yeah, 1,023. So just 5 hours, you've got 1,000 of them, those little suckers. Just divide and make more, just divide and make more. How about 12?
16,718,000.
Yep. So 1.386 times 12. And you have approximately 16,718,058.
So is Alex gonna want us to round to the whole number?
I will I'm sure it will specify. Yeah, I'm sure it'll tell you. It often does in other questions, doesn't it? It tells you what to do. I'm sure it'll specify. So if you're having problems with it, just screenshot it and email me and we'll figure it out. But my suspicion is it wants you to round to the nearest whole number in cases like this. It's crazy. And obviously this probably isn't going to be true eventually. Like this thing probably won't grow like this crazy speedy forever, right? It might eventually have a limiting value where it kind of like levels off because it's either killed everyone off, people are actually immune by now. Yep, that's called a limiting value. And we'll also talk about some things that have that in this lesson, okay? But at least on an initial scale, like to start, initially the growth is exponential. So when you talk about these models, you often talk about them like, okay, it's exponential for a little while and then the pattern changes and becomes something else. That's why you don't do what's called extrapolation. Don't go too far outside your data. Like you wouldn't want to put in 100 years for this. Does that make sense? It's way too far away. All right, now the next thing we have is half-lives. So radioactive elements. So suppose you have an initial amount of some half-life, and the amount A is given by this equation. So let's think about what was the doubling equation. The doubling equation was A equals A naught 2 to the, I said X over, this was double time, right? That's what we had for that equation. I think I'm going to use P instead of A naught, but whatever. How is this one different? You got a half instead, right? Does the fact that they use T instead of X really matter? What does the H stand for? Half-life. So what are the essential important differences in these two formulas? There's a half versus a 2, right? Other than that, they're pretty much the exact same, aren't they? You have your double time, you have your half time, right? So in a different lesson that I've used for this kind of topic before, I had the example of Chernobyl in Ukraine that exploded in, what was it, 86, I think? So I don't know which one, but one of the elements, I think is pronounced cesium, but I could be wrong, because I'm actually not a chemist. Suppose that there were just 100 kilograms of it sort of that got released in the atmosphere. This one's really dangerous. And let's suppose that the half-life is, let's say, I think it's 36 years, but let's just make it easier and say that it's 30 years, okay? Let's just explain to you why the formula is what it is. So at the start, how much do you have? 100. At year 30, you have 50. And at year 60, you have 25. At year 90, right? Just how much you're going to have?
17.5.
12.5. But yes, does that idea make sense? You just keep halving? The formula that you'd make for that is you start with 100. I'm just going to say 0.5 instead of 1/2, but the same thing, right? You need to multiply by 1/2 once when you plug in 30, right? That's why your power is t over 30. Because when you plug in 30, multiply by 1/2 once, right? When you plug in 60, multiply by 1/2, how many times? 2 times. And 100 times a half makes the 25, right? When you do 90, that's 3 half-lives, right? So it's the exact same formulation as the whole doubling time thing, except for there's a 0.5 because you're halving. Okay, so here's one of the radioactive things. So you use gallium-67 to diagnose malignant tumors. It has a biological half-life of 46.5 hours. So if you begin with 100 milligrams of this isotope, how much is going to be left after 24 hours and a week? So first of all, what's the general equation? So it's A sub 0, 0.5 to the, we'll say, T over H. So what goes in for A sub 0? 100. 0.5. What goes in for H? 46.5, exactly. And in this thing, since our half-life was in hours, the units of our time are also hours. So to figure out 24 hours, you plug in 24. So A will equal 100 times 0.5 to the power of 24 divided by 46.5. So go ahead and calculator that and see what you get. It should not be halved yet, right? Because 1 half-life hasn't gone by. Anybody dare to get an answer?
69.92.
Perfect. 69.92. How would you figure out a week?
Calculate how many hours are in a week.
So how would you figure out how many hours are in a week? There's
4 hours every day.
7 times 24, exactly. I think that's 168. Okay. So A will equal 100 times 0.5 to the 168 over 46.5. This is how they figure out when it's safe to give you more. Does that idea make sense? Probably also err on the side of caution in case there's something, but I got 8.17. Did you guys get that? 8.17 milligrams.
When they say whether or not it's safe for you to go, it's because the half-life is
Yeah, and that will depend on how much, because they're gonna add more to your system, and there'll be a little bit of trace elements left, right? And so I don't know the specifics about how much of this stuff is safe because I'm not a doctor. But what they probably do is they say, okay, well, if I add 100, is 100 plus this 8 gonna be too much for your body to take? Does that make sense? So they wait until this number is low enough that adding more won't hurt you, or won't hurt you as much as the cancer might. Okay. So just like sometimes those population questions could be written with ease, these can also be written with ease. I'm not telling you how to do that quite yet. This is a specific model for carbon-14, which is often used in carbon dating to figure out how old stuff is. If I'm remembering correctly, I think its half-life is about 5,000 years. I don't remember exactly what it is.
It's relatively close.
It's pretty close, yeah. It's like 5,400 or something like that, I think.
So the longer your half-life is, the more accurate your time will be, because as something decays, the closer it'll be.
Well, and I think to date things that are really, really old, they actually need things that have even longer half-lives than that. Like to date like dinosaur fossils, they have to use something different. So, but the point is that this thing has a half-life of 5,000 years. So, and you can figure out that this is an equation for that involves E. And so if you have 1,000 milligrams of carbon-14 that's present in a recently deceased animal, how much is going to be present in 10,000 years? And I have some kind of cool questions I'll try to bring in that you know how much carbon-14 like a skeleton has, and you can figure out about how old it was. Like, so is it a recent death or is it an old death? Does that make sense? You can figure out, was it a murder or was it somebody that died 1,000 years ago and they just happen to find their body? It's kind of cool.
Wait, so we're supposed to know that, like, off the top of our head?
Nope.
it's 5,000?
Nope, you wouldn't. I would tell you. Does that make sense? But the thing is that whole idea of the half-life being 5,000 years can be rephrased to involve this E. Does that make sense? And the half-lives, the amount will go down over time as decay, right? How you can tell that this equation is decay is that the E's exponent is negative. That means it's going down over time. Okay, so 10,000 years. What goes in for the A sub 0? 1,000. E to the power of negative 0.123, 124 times 10,000. I have a hard time keeping track of my zeros, so I actually have to count them out. So plug that in a calculator and see what you get. I got 289.4. So my half-life of 5,000 was pretty darn close, because if I had 1,000 to start and went if the half-life was 5,000 years, half of that is 500, right? Half it again and you get 250, which is pretty close to 289, right? Okay. How would you figure out 50,000 years? Plug in. What goes in for T? 50,000. So 1,000 e to the negative 0.000124 times 50,000. And I got 2.03. See if you also get that. Great. 2.03. On your calculators, there is a way to edit the thing that you previously wrote. Okay, does that make sense? So if you don't know how to do that, ask me for class and I'll show you. I think there's like an up button of some sort you can push, and it will give you the previous thing you entered, and you can just change the 1 on the 10,000 to a 5, which will save you a lot of time as well, right? Okay, awesome. All right, so now the next thing we're going to talk about, last thing before we're done, is how do some of these models look if you have these like limiting values where the population or something, say like it grows initially, but then it kind of levels off and has what's called a carrying capacity of some sorts. Okay, so this idea is that a company is trying to expose as many people as possible to a new product through television ads, and the area has 2 million potential viewers. A model for the number of people in millions that are aware of the product after T days of advertising is given by this. And so the question is how long should you bother to advertise, before you've told enough people? Like, you're not gonna get to me because although I have a TV, I lack the capacity to watch TV shows on it because I don't have any kind of converters and stuff, and I just don't have the time. So, how many viewers are gonna be aware of the product after 2 days and after 10 days? Okay. So after 2 days, you'll plug in 2, right? So 2 times 1 minus e to the negative 0.037 times 2. And because I think you're good enough at plugging stuff in, I'm just going to tell you what that is. I got 0.143. And this is in millions. If you want to give an answer as an integer, how many places should the decimal move over? 6. So move over 6. So that's, I'll say mil for millions, is 143,000 people. Does that make sense? Okay, so when they say they want an integer, they mean that they want a whole number of some sorts.
Why do we move over 6?
Because this equation measures the number of people in millions.
Oh, okay.
So it's 0.143 million, which is the same thing as 0.143 times 1 million, which is 1 followed by 6 zeros. And multiply with something that has 6 zeros, move the decimal place to the right 6 spaces. Does that make sense? Okay, awesome. So how about 10? So for 10 days, you plug in 10, right? 2, 1 minus e to the negative 0.037 times 10. For that, you get about I got 0.6185. Does that round up or down? This 5 means that rounds up. So 0.619. So what would that be as an integer? 619,000. Okay. So after 10 days,
So we just round up, because if we times that by million, then it would give us like a bunch of numbers. But we can round.
yeah, but they also say 3 significant digits.
Oh, okay.
Does that make sense?
Yeah.
Otherwise, you would use the additional digits. Yep, no, great question. Okay, so question B has to do with that whole idea that as you plug in bigger numbers, there's a definite capacity. You can't reach than 2 million people because there's only 2 million people in this community, right? So does A appear to approach what's called a limiting value as T increases without bound? That means T goes to infinity. So this A is the same thing as 2 times 1 minus, I'm going to rewrite that as 1 over e to the 0.037t. So does it make sense that that is the same thing as the first equation you're given? Negative exponents are punished and they're set in the basement, right? So as t goes to infinity, does it make sense that e to the positive 0.37t also goes to infinity because it's exponential growth? So what will happen to 1 over a big number?
0.
It'll go to 0.
And 1
You-
minus 0.
And 1 minus 0 is 1. So the limiting value is 2 million. And that should make sense in context. You have 2 million people. The longer you have your ad out, the more likely you're going to get to all of them, right? But you can't get above the total population in people who have been exposed to this ad. So that's the idea.
Wait, so we're just plugging it in 0, or?
Nope, the idea is you're plugging in humongous numbers for t, or taking this t to infinity, and that means that this expression, this 1 over e to the stuff, will go to 0. You could also think, another way to think about this is that this e, that's a decay picture, right? So that E part alone is gonna look like this, isn't it? And as the X gets larger, it gets closer to 0.
Oh,
So the thing to say is that this piece is gonna go to 0. So that's what's meant by like a limiting value.
so then 2 times 0 would be 0, but we're just saying that,
Yeah, it's 2 times 1 minus 0,
oh,
which is 2. So that's one way to do these kinds of questions. The next one is example 10, which is something I call logistic growth. So I assume we'll talk more about these quiz later, but this curve models the spread of a disease in a community of 1,000 people. How many people have the flu after 10 days and 20 days? Let's just do 20. So here's the one thing I'll be a little bit careful about. When you punch this in a calculator, you have to put your denominator in parentheses. So like it should look like this. And assuming you do it right, that should give you approximately 288 people are sick of the 1,000 after just 10 days. Oh, sorry, 20 days, excuse me.
It's like 1/4 of the population.
Out of 1,000, yes, the quarter of the population, yep, exactly. So the one thing I'll talk before you go is the limiting value idea. But does it make sense how to plug numbers into this function if you're given it? Okay, that part's not very hard. Now the second question is, does this appear to approach a limiting value as t increases without bound? So let's rewrite that as 1,000 over 1 plus 999 over e to the 0.3t. And this part, as t goes to infinity, this goes to 0. So the limiting value, is 1,000 over 1 plus 0, or 1,000, which is the size of the population, right? You can't get more than everybody sick eventually. So that's the idea.